Cool. Hello everybody. Welcome to April's OARC monthly talk. Tonight we have Derek Cazell, Mike Whiskey Zero Lima November Alpha, who's going to teach us some advanced VNA use and show us all sorts of tips and tricks, and hopefully do some nice hands-on demos as well. We'll have a talk from him for about 45 minutes, and then hopefully we'll have about 5 or 10 minutes for questions afterwards as well. And we'll lead up into pub at 8 o'clock for anybody who wants to join us for that on the Discord. Couple of housekeeping notes before we start. If anybody wants to unmute and turn the camera on during a question and answer session, that's absolutely fine. If anybody doesn't want to do that, feel free to put questions in the chat for later. I will take those and I will funnel those onwards. We'll have details about next month's talk at the end. I don't like previewing talks before someone speaks because that never seems fair. And the only thing I will say is I am still looking for talks for June's Flash Talk event, where we have a number of 10-minute slots available for you to come and tell us about anything that you think is particularly cool or interesting that you'd like to share with us. So, that is all the housekeeping I have, and we have a lot to go through. Hello to everybody who's joined us for the first time. Thank you for coming, and we'll try and carry on doing a lot more of these as we go through the rest of the year. For now, though, I'm going to hand over to Derek.
Thanks, Mark. Hi, I'm Derek Cozell, MW0LNA, and my background has largely been software-defined radio, but the inevitable outcome of that is that the software ends up only being maybe half of the system. Beyond that, we hit the dirty world of hardware. And when it comes to RF, one of the key tools of getting any job done, really, is the ability to see what's happening inside of the system. With my background in GNU radio, my bias has always been that you can just drop down, a frequency sync or a time sync. These are the equivalents to see what's happening within the circuit itself at any point. In software, that's really easy. We can just copy off the data at some point, save it to a file, or plot it in real time. What do you do in hardware? Well, most of us are probably already familiar with things like a multimeter, which is able to measure a voltage at a very slow rate, a couple of times per second. We can probably pin me. Can you pin me, Mark, as a full screen on it, or do I need to kill sharing for that?
I would have thought that's one of those things that is user's choice, to be honest. I will have a play and I'll see what I can do. Yeah, I think people can pin people themselves. It's always user's choice on the interface, guys. I think.
Yeah. Presumably, if I, just stop sharing, you'll end up with a larger version of me, hopefully.
You can totally do that and reshare if you want. That's no problem,
Yep.
Derek.
Grand. So within a system, we have the ability to look at using something like a multimeter, where we can see voltage or current measured at a specific point in the circuit at a fairly low speed, a couple of samples per second. Now, one of those concepts that we get from the software-defined radio world, and from places well beyond that, is the idea that if you are sampling some piece of information at a fixed rate, we can take that information over time and transfer it into frequency. And so what's your software-defined radio doing? It's sampling the voltage or current, tens of thousands, hundreds of thousands of times a second, and transferring it into frequency, and then we can plot that data. So a multimeter done faster is your software-defined radio. But what else do we have in terms of tools? We have spectrum analyzers, a very convenient tool for saying, what's happening in the frequency domain at this point in the circuit. Normally we're attaching that, you could attach that to an antenna, and then you've just made, basically a fixed waterfall receiver with no demodulation capability. Or we can attach it to the output of your system, and then we're looking at what your transmit signal is. We could take a device like a directional coupler, tap off a very low power version of your signal, and see what you're broadcasting, but without interrupting your ability to transmit. A whole bunch of different scenarios where you might use a spectrum analyzer. But that lets you measure the power. But what if we wanted to say something like, how good is my coax? How good is this antenna actually working? Well, we might do something like take a broadband noise source, something that's going to emit RF power at a very, very wide range of frequencies. Turn that on. And this is, if you've ever measured a low noise amplifier using a noise source, that's what this is. And then take a spectrum analyzer, turn it on, and we'll see the behavior of the system. If there's a bandpass filter, we'll see the noise only pass through within a narrow frequency range. Okay, so now we've got the idea of power into a system, and we can see some of the information coming out the other side. So finally, we're getting towards a vector network analyzer. I will start sharing again because this is where I have pictures, and they hopefully explain 1,000 words. Come on, give me back. Okay. Hopefully that screen is now sharing and it's floating. Oh, there, my screen. Wonderful. So beyond standing wave ratio, a hands-on introduction to VNAs, impedance, and time domain reflectometry. This is the talk title that I gave to Mark months and months ago, and the talk that I'm going to present is approximately within those bounds. I definitely encourage questions. I have the chat up on a screen, so throw them out as fast as you can think them up, and I'll try and address them live in time. Starting, I'm going to start off this with a really fun video that I think is something that everybody should go and watch, but it's 26 minutes, and you can do that in your own time. But hopefully this will work and you'll be able to hear this. I have not actually, we should have tested this, apologies. But this channel called Alpha Phoenix has this great demonstration of what it looks like for voltage to move along a wire. In this case, a twisted pair of wires, and he's measuring the voltage at different points in it. You can see that he's created these very, very long racks and taken all the wire and twisted it back and forth. This is because the wire is conductive and he didn't want shorts. What does he have? He has an oscilloscope and can tap out the voltage at various points.
For example, what if I wanted to know exactly how fast this switch is? When you plug in the battery, how quickly does it...
Derek, sadly, we can't hear that. You might need to tick the little box to share your system audio when you share.
Okay, thank you. Leave computer audio settings. In any case, the audio, yeah, is probably coming from...
I think
in any case,
I
kind of want to narrate over him anyways, so I'll just mute him and hit play anyways. So he's got this. There we go. He has put a voltage source onto this wire, and guess what? Over at a certain time, the voltage rises from 0 to 2.5 volts. Your standard kind of lithium-ion battery voltage. And he, can do some measurements and say, oh, the rise time is this and this. How fast does this voltage actually rise? We can see a little bit of ringing on the signal. But the cool thing that he does in this video is he then moves that oscilloscope point down the line, a centimeter or so, and captures the data again and again and again. And that... he starts doing, this is, I think, when he's running around, he's broken his wire a little bit. And what he has is a very, very long wire here. And then he's split the wire into two places, goes down a long rack, and in one point he shorts the two ends, and the other he leaves them disconnected. In the RF world, we think of this as, an RF short or an RF open. It's the same thing at DC as it is at RF, except in how the system actually behaves in a very short time period. He works his way through, and we get to the really great animation here. Sorry. We will paste this link so that people can watch it. he turns it on, and you can see this great animation of the voltage rising as the signal goes out. We can see that the time scale here is 250 nanoseconds, so an extremely short time. This is the concept of propagation delay. If we think of light moving through air, we have the speed of light in air. This is the speed of electrons, speed of voltage moving down the line, moving down the copper conductor in this twisted pair medium. It's taken approximately 250 nanoseconds to go through this many meters of wire. And if I hit continue here, what we're going to see, and what we can start to see already in this trace, I'll use my mouse, the voltages come in, it's split off, and it's been an equal voltage dividing either direction. We have an equal voltage divider. And as it's hit the short, the voltage is forced down to 0. If you've connected two wires together, the voltage can never be different. It's always going to have to be 0. On the other side, with an open circuit, all the electrons are piling up, and we're getting a surge in voltage right at that point. And as this continues, we can see some kind of wave it's reflecting like a wave. And I realize this is probably fairly confusing to some folks, but we'll get there. This is the motivation. And here's it all nicely actually plotted in a much easier way to see. So at time 0, he's going to flick the switch on the battery, and we can see the voltage surging through. The voltage surges down the line, hits the reflection, and the voltage has to split. There's just only so many electrons, so you're going to get less on either wire. And we can see that it's split down. It hits the end, the short stays low, and the disconnected goes high. For folks who have seen this, we can basically think of this as the phase of the wave is either inverting or not here. And as it flex back, we get this nice propagation. What's the big takeaway that I want people to have here? One, this is a really cool animation. You should watch the 26-minute video. The other piece is that energy flows as a wave down a line. And there's plenty of great material in his video, and he has impedance matching and other pieces as other video concepts here. But we will leave that for you to watch after the pub. We don't need that twice. So why a VNA? We've got power moving down a line. One of the fun things that you kind of get is we know that there's two different concepts here, at least when it comes to a wave. We know that we transmit power at like 1.8 megahertz, a frequency, and we transmit a certain amount of power, 10 watts worth of power. We have an amplitude, which is the A in this piece of equation. And then if you aren't already familiar with it, just take it as kind of an assumption that e to the j at kx is representing a sinusoid. It's representing a frequency, a circle. As we progress in time, this would rotate around at this value would create a sinusoid, a sine wave. And so as we move forward in x, in distance, the sine wave goes up and down, but it has the same power. The A term doesn't change. And this is sometimes counterintuitive if it's your first encounter with it. You might be looking on an oscilloscope at a trace and seeing the sine wave going up and down, but it still has the same amount of power even when there's no voltage present. And if we looked at the current, we would see that is in different phases. So looking at a wave, we have a wave traveling forwards. And then in this case, the circle with the sine wave symbol in it is a generator. This is your standard radio transmitter. This is an RF signal source if you have test equipment, etc. Or if you have a function generator and want to do this at low frequency, then it would be something like a function generator where you could generate 1 megahertz or 100 kilohertz sine waves. This is attached to two generators together, and we can actually see that it's forcing a wave backwards along the line. Does anyone know what happens if you have two signals that bump into each other on a line? Comments in the chat, as a YouTuber might say. Yeah, annihilation, addition, they combine in whatever that is. If they are in phase, if the sine waves are overlapping, they will add up. If they are out of phase, they will collapse, and you'll get a reduction in the wave at that point. And if these are happening at the same frequency, what you'll actually end up with is partially a standing wave ratio. And this is the ratio of how much they combine versus how much they subtract together. I'm holding my hand up to the screen like you can see that. If A2 was 0, there was no reflected wave, then all the power would move forward and vanish off somewhere on the right hand of the screen. We would have a perfect match. All of the power being transmitted out would vanish off into the ether, hopefully into your antenna, hopefully being transmitted. If we had no power, if we had an equal term, A1 equals A2, then all the power would go forward and we'd be seeing the same amount of power coming backwards. And in that case, we'd say, okay, well, not much is happening here. All the power is equalizing itself. We have as much going one direction as the other. Now, it should hopefully be fairly obvious that most of the time it's a really bad idea to connect two radios directly into each other and transmit both at the same time. Don't do this with test equipment either. It ends up as a very bad time. We all know, well, hopefully folks are familiar with the concept that if you don't connect your antenna to your radio, it's going to blow up, or you might cause damage to the output. Why does it cause damage? Because all of that signal that you're transmitting out reflects backwards. That's the core idea. We want to be able to measure this ratio. And so what does this circuit look like? We have current, we have voltage heading into some device. This could be an antenna, in which case it would be one port, just I1 and V1 here. Or it could be something like a filter, which I have here, where we have SMA connectors on either side. And this is a flight-aware, 1090 megahertz ADS-B filter that should be a bandpass. We'll measure this shortly here. And that's a 2-port. It has voltages and currents that we could measure on either side of the device. What does that look like a bit more complicated? Well, we've got port 1, which has an A wave traveling into my filter, what other boxes have I got around here? Well, this is a bad, I'll hold it so you can't see the third port, but some little block filter or resistor or attenuator. Got plenty of those around, where we have 2-port devices. So we have power traveling into it. Some amount of it's going to reflect back. It's really, really hard to create a 50 ohm coaxial connection at all frequencies. At some point, you're going to get a little bit of a mismatch, and some of that energy is going to come reflecting back, like we saw with the piece of the video with a short or an open. That's the farthest ends of where this could be. But if you get a little bit of a mismatch, you'll still get some of that wave reflecting back. So we have an A wave, a B wave, and then on port 2, we have the same thing. A again heads into the device, and B heads out of the device. And so what does this look like practically? I think okay, we'll stay on this one. If we had something like an attenuator or just a lossy, real piece of coax where you lose a bit of power as it goes in, but let's say it's really good quality coax. A1 is going to be a big value. We're transmitting 1 watt of power or 100 watts or 400 watts of power into this piece of coax. B1, we hope, is very small, not very much power coming back from it. Our coax is good, most of the power is going to go off to the other end, and we hope we've connected it to a good antenna. A2 should be really low as well. We're hoping that there's not really anything coming back from your antenna, unless of course you're receiving, but let's consider transmit. And B2 should be really big. Most of the power we put into the coax should be going out the other side. So what quantities do we actually care about here? We care about our S parameters. These are our scattering parameters, and they're what you measure most of the time with a VNA. We'll see that SWR is kind of a different form of these values. S11, the S parameter from port 1 or to port 1 from port 1 is how you read that, is B1 over A1. So what is that? That's the return power, how much power is reflecting backwards from our input port, over how much is going in. So if B1 is very, very small, A1 is very large, S11 will be a very small value. Not, we have a small value divided by a big one. S21 is the power or the voltage or the current, but usually we speak in terms of power arriving at port 2 from port 1. It's that B2 wave exiting divided by the A1 wave entering the other port. So how much power goes straight through? If we're thinking about an attenuator, then we're expecting, the one I'm holding is a 20 decibel attenuator. We're expecting the power to be 100 times smaller, 20 dBs of attenuation. So the B2 wave will be 100 times less than what's going in. If we have an amplifier, which is connected to a power source, so hard to pull up, but I have a small amplifier here that I think has about 15 dB of gain. We would expect the S21 to be positive. The B2 wave is bigger than the A2 wave. And running through the other terms, we have our input match, S11, our output match, S22, B2 over A2. So how much power is going out versus coming in of port 2, and the other way around. How much power is going backwards across your device? The power at port 1 compared to port 2. We'll work through this, kind of as continuous concepts. So what does a vector network analyzer do? It says, okay, let's take the radio out, let's take the antenna out, let's focus just on being able to measure one component at a time or one part of a system at a time. And that could be your radio, it could be your antenna, it could be the coax, but let's put synthetic sources on. So it includes an RF source, something that's able to send out an RF signal. Now, I mentioned at the beginning the idea of using like a really broadband RF source, noise source that kind of gives equal power at all frequencies. That turns out to be not particularly useful all the time, because we're putting power out at a lot of different points that we maybe don't want to measure. It's hard to get a lot of power. Try imagining putting out 10 watts of power at every frequency between DC and 10 gigahertz. You'd have your own power station at that point. When we could do almost the same thing with just one sine wave. And so something like the NanoVNA, and essentially most modern, or most historical VNAs, I should say, as well as many that you would buy today, will just put out one frequency at a time. They'll put out a test tone, switch it to port 1 or port 2. With the NanoVNA, an interesting point is that it can only put power out on port 1. And the first thing it goes through is a coupler, and it samples off a small amount of that transmitted signal. And it considers that its reference. Then as the wave goes outwards, it hits port 1. And let's say that we'd attach this just to an antenna. We're not going to be able to measure anything at port 2 because an antenna only has one port. So the only thing that we can measure is the amount of power reflected backwards, S11. So the power will come backwards across, go back, and we'll receive through another coupler power into port 1. And this gives us our A wave and our B wave. We divide the two, we get S11, and we can plot that out. At that frequency, we can tell you how much power went out versus how much power came back. Now, there's a bit of a fun trick to this. These aren't only measuring power, they're also comparing the phase. And so they can tell you not only how much power came out and how much power came back, but did it go just into a resistor where power gets burnt, but there's no phase shift? Or did it go into, was there a capacitor out at the end of the line? A capacitor will introduce a phase shift because it can't go from 0 voltage to infinite immediately. And so you have to dump a bunch of current into it first, and it changes the phases. So that's a poor explanation that I'll try and nail down a little better later on. we've got our S11. On the NanoVNA, we can measure only the power coming back into port 2. So we can get this S21 parameter coming back across and into port 2. And so this is what we call a kind of 1.5 port VNA. And if you have a NanoVNA yourself, you can look on the front. I'm sure this won't show up at all, either through my camera blur or through the screen, but you'll see that it actually has the labels on it. And noting the time, I need to put foot on the gas. So where does this actually start coming into? You're probably familiar with this point, and I've rattled on for 20 minutes about things you're mostly familiar with, or maybe seem a little bit like the nitty-gritty details that don't really matter. Where do they start mattering? You have to calibrate your VNA. Why do you have to calibrate your VNA? Because we want to measure what's actually happening to our device under test, the thing that we're attaching the VNA to. But what's the first thing that you do to a VNA? You attach some cables to it. Do I want to measure these two cables? No. I want to measure my attenuator. I want to measure my antenna. I want to measure a filter. So how do I both tell the device that the thing I want to measure is actually, 2 foot down the coax, and the coax is a little lossy. Sorry, I didn't spend a huge amount on it, so we're going to lose a bit of power getting to and from the device. And it's got distance, so that sine wave is going to shift in phase from where it is at the edge of the NanoVNA or the VNA port to where it goes out. We see this, the generator, it has its own characteristic impedance, 50 ohms for basically all the VNAs that any of us are likely to see. And then there's some amount of distance. And we want our reference plane where we're calibrated to be right up against our device. This will no longer be 50 ohms. We'll have lost, our coax may not be exact. We might have gone through switches and other things to get out to that point. We might have climbed up ladder line or something like that that doesn't have a 50 ohm reference. And so how do we get that calibration? Well, we have to account for a whole bunch of different errors that happen along the way. This is a ton of different terms. Hopefully somebody finds it interesting, but this is basically the 12-term error model. And this is what we're solving for when we do our calibration. We want to know, as we're putting power out, how much of it just kind of loops right back. If you've ever, what's a good example? If you ever unplug the antenna from your HT and then have somebody transmit right next to you, you're probably going to be able to hear it anyways. There's signal leaking straight through your device, not just through the coax, but straight through the case, through the shield of the coax, right into your receiver, into the circuit. So we have some forward leakage. We hope that all the power going forwards is getting there, and that there's some accounting for the loss. We have power that's kind of bouncing back, leaking from port B backwards. We have power being lost as it's coming back to our receiver. We have power that's jumping over our device under test. If I put a 100 dB attenuator between the two ports, power is going to jump right over that to a certain degree. Same thing with on the B port, some of the power will reflect back that has to do with the second port. And we get the same thing all on the other side. There's 12 terms in total. You can go fancier, but the standard model has 12 error terms. We need to set up a bunch of known references that will let us solve for all of those unknown values. The standard that we end up with a lot of the time is called short, open, load, and maybe through. If we're only doing one port of measurement, we can use small calibration devices, little single port pieces of hardware, which very, very carefully are engineered to give us as close as possible to an ideal result. And so our load, for instance, will be a 50 ohm load. It's basically, pretty literally, is a 50 ohm resistor. Although, for fun reasons, often it's actually a couple of 100 ohm resistors or 200 ohm resistors split across, because you can get lower capacitance and lower inductive imperfections that way. So consider it a perfect 50 ohm resistor for the moment. All of the power sent into it will just vanish if everything else in the system were perfect. What you'll inevitably see is that you attach this to an uncalibrated VNA, and it won't be a perfect point on the Smith chart, or it won't be a perfect 100 1-to-1 SWR. There won't be all the power going back. Some will come back, and the VNA measured that and said, oh, okay, this is my imperfection. We can put an open on it. An open should give us that reflect that we saw at the very start of the video, where there's a high voltage swing and it comes back. It'll impose a very known phase shift on the signal. The same thing happens with the short, but it's opposite. So we're able to explore the space and solve both of those pieces. So with short, open, and load, we can solve 6 of the terms that deal with just one port. You do the same thing on the other side. Sorry, not full 6 terms. You can solve a bunch, all the ones that are relevant to one port. You do the same open, short, load on the port 2, or port 3, or port 4, depending on how much money you've thrown at your VNA. And you can calibrate all of those ports in isolation. The only thing you need to know now is, well, what happens if you connect them all the way through? What additional term is there if you actually connect a device between 2 of the ports? And so we put a through, what should just be a perfect piece of coax through. That's all of our calibration. Using that, you can solve all the equations. There's some really fun Python code and formulas that you can go through. And if anybody's interested in that, I can definitely share a spreadsheet as well as a bunch of recordings of, from a raw VNA of these perfect references. And with those, you can solve out and create a calibration file. So where does this get us to? Long way around, we have some plots that look like this. This is a program called NanoVNA-Saver, runs on Mac, Windows, Linux. And if I hit sweep, we'll see just unconnected ports, but it'll clean up a little bit. What are we looking at? Hopefully, most folks are kind of approximately familiar with some of these concepts. Here we have our S11 return loss. I just have some coax going to an open right now. And so what we're seeing is that only about 3 dB of power is being lost at low frequency. Then that loss actually decreases as we go up to 250 megahertz. It goes down, it goes back up, it goes down, it goes up. This is raw and uncalibrated. But we're seeing that essentially most of the power is reflecting back at most frequencies. It's an open circuit. There's a bit of coax. It has a certain length, and so it resonates. But we get that. Our gain is very, very low, minus 80 at low frequency, and then it goes up. What we're seeing here is actually the limitations of the NanoVNA more than how much is leaking through the air between my 2 ports. But basically, there's no forward power, very, very little. Then we get into the Smith chart, which will be a little bit deep to explain if you've never seen it before. But the fun bit that you can kind of approximate it as is the center of the plot, whenever we're going to be seeing it, is 50 ohms. You can actually adjust that. So people who were working in 75 ohm based systems, for instance, the center of their plot would be 75 ohms. But every time that we're going to deal with it, pretty much, it'll be 50 ohms at the center. As you move outwards along the center line, you're changing just the resistance. And so what you end up with is, okay, double check my bits. Can I get a better plot than what I have here? Yeah, that's a better plot. So what we have here is basically our 1-port scenario. We have our 50 ohm source resistance and some unknown load resistance, ZL. we're measuring our incident and reflected power, and we can calculate that out and get what our actual value is. The center impedance matched would be if this was 50 ohms and the other was 50 ohms. As we move to the left, we get a short circuit. So all of the power is reflecting, and we're getting 180-degree phase shift this direction. If it was the other way, it would be an open circuit, and the phase would also be kind of 180 degrees, but in the other direction. What gets fun is that as you go up or down, you can measure capacitive or resistive pieces. And so as you move up, basically it lets you measure the behavior of the system where, not just how much power is there, but is there a phase shift one direction or the other. Getting through, this is all uncalibrated. If you're on a NanoVNA and you go through the menus, I think there's actually a screenshot option. Yeah, the plot looks like this on a NanoVNA. So we've got our S11 in log magnitude. That's this style of plot where it's log because we're on a dB scale. So as we go down by 3 dB here, we know that we've lost half our power. If we go down another 3 dB, we've lost half again, and that compounds, so it's logarithmic. The Smith chart is on the background here. We can see the same curling behavior. The phase is shifting as you move in frequency, and then we've got some error happening here at the edge of the frequency. S21 in log mag in phase, which we're seeing here as well. Grand. So what do I want to do at this point? I want to actually calibrate. And this, unfortunately, is a little bit hard to go through. But basically, on here, you tap into the calibrate menus. We can do this through here as well, which, to be fair, we could go that route. But basically, you get a slightly better result if you calibrate on the device. So what you want to do is set up your sweep range in frequency, because I kind of jumped over this, but I said the NanoVNA measures at one frequency. Well, that's one of these individual points. So what does it actually do? You say, I want to start here. I want to go to the stop frequency. In this case, I'm going from 50 kilohertz to 1.5 gigahertz, and I'm going to sweep through that. We can see I've got 401 points that I'm going through, and that ends up being, I'll measure every 3.75 megahertz. Now, if you're measuring an HF antenna, that's terrible resolution. If I'm measuring something like a bandpass filter, I don't really know where that band might be, or I don't know how big it is. This will let me just see the maximum that the device allows. So set your sweep so that you're going to get data, lots of data points within your area of interest. An interesting point on the NanoVNA specifically is that you need to hit the reset button first. So if you go into the calibrate menu and you hit reset first, that clears out the calibration that might have been there before, and you can start plugging in the pieces, starting with an open. I'll start running through these. If folks have questions up to this point, please throw them into chat. I know I'm terrible with timing. I apologize. So we're 40 minutes in, and
Derek, we can go to 10 too if you want.
cool. We'll go to then, so that at least I can show you the time domain reflectometry and a couple measurements of these filters, so you can see what these look like on the various plots. So I've just done an open, a short, and all I'm doing is taking these coax loads and screwing them in to the appropriate end of the coax. Does half take its time. You'll see that there's an isolation parameter there. They only give you one load. Isolation technically should be done with 50 ohm loads on both of the coaxes, but what you can do instead is either just skip it or just put a 50 ohm load on one of them, leave it there and measure isolation, and you should get, at least a workable result. one of the things to definitely know is that the NanoVNA is frankly a terrible VNA, but it's amazing for the price value. One of the big things that it fails at is stability. So this is not a device that you calibrate once, throw in your bag, and use forevermore. You should be calibrating a NanoVNA at least every day that you're using it. You need to recalibrate it every time you change your frequency range. And if it changes in temperature by a bunch, if you go from a cold house to a hot weather outside, up on a roof, or you leave it out in the sun, all of your phase information at least is going to become garbage. If you're only measuring, how much power is reflecting off an antenna, maybe that doesn't matter. But if you're trying to do something like measuring the matching network and you're going to be adjusting impedance, adjusting capacitance and inductance and stuff like that, you need to be recalibrating. So I have just completed the measurement. I'm going to put a 3 dB attenuator in between port 1 and port 2, and hopefully we'll get a nice clean trace. Well, actually, I'll leave it unconnected for the moment. So if I hit sweep, hey, cool. We can see both that this works and that this is a terrible result. So right now I just have a 3 dB attenuator on port 1 with an open at the end. I've not connected it to anything. So I should have asked this question before I hit the sweep, but can anyone explain, or can anyone make a guess why this is measuring -6 rather than -3? And this is the S11 return loss plot. Yeah, loss in both directions. We have a reflection. We have ideally a total reflection out at that open circuit point. The power is going all the way through the 3 dB attenuator, dropping 3 dB, hitting that open, and reflecting straight back. And it incurs another 3 dB of loss. So that's really useful. That's fun. And we can see we've got 3 dB of loss. The rest of it is, and because it's reflecting back, we can see that it's not actually at 50, it doesn't measure as a 50 ohm device. It measures as something between 50 ohms and infinite resistance. Or, yeah, that's the right direction. Anyways, we're not getting a well-matched device. So now I'll connect it straight through, and on the gain through, again, we're seeing essentially no power come through. It's still sitting, -80 to -50. What we can see, though, actually I should emphasize this, is we can see that because it's an open circuit, it stays at basically exactly -6, within essentially measurement error, up to 250 megahertz, but then we start oscillating. And this is getting more and more reflections. And you could actually, as a fun thing here, you could measure the distance between these peaks, and that would tell you some information about how long this piece of coax is, because it does have a resonant length. But that's not really the point. Here's a much better plot. This is our 3 dB attenuator connected between both ports. So it's straight through at the moment. Our gain correctly is measuring at -3 dB. That's staying, NanoVNA again is no prize pony, but we can see out to 500 megahertz or so. That's probably pretty clean. I didn't pay particularly strong attention to how I was handling this. One thing we'll kind of note is I have a big coax bend here because these weren't very long leads that I put on. By bending that, I have shifted how the coax is behaving. That calibration is now no longer totally valid. But we can kind of see it's decent up to 500 megahertz. And our return loss is very, very good. Almost all the power going forwards is not coming back. We're well below -20 until we get out to kind of set 400 megahertz or so, which I can click this point, marker 1, so there's 450 megahertz. We still have less than 1/100th of our power being reflected back. Some of that has to do with just the NanoVNA isn't a perfect match. It is really only designed to go up to about 300 megahertz, so it's exceeding the range where you could say it works very well. This one does claim to go up to 1.5 gigahertz, but it's pulling all sorts of cheats to get there. They don't actually have a signal generator which can generate a 1.5 gigahertz signal, much less a 600 megahertz signal. What they're doing is they're using the second harmonic and then the third harmonic and potentially the fourth harmonic of the signal generator in order to look at the signal. What else do we see? We see a very nice tight curl right around here. If I drag this marker, actually these markers are all moving synchronously, that's nice. So that red marker we can see is staying right in the center. The impedance that we're looking at is 46 ohms at 306 megahertz. It models what it would look like if there was some series inductance, which we've got a long piece of wire, or we've got a piece of wire here at least, so no surprise it has some inductance. Here it's actually saying it has a negative series capacitance, which is kind of neither here nor there. It's also a very small value. If we looked at it as, we'd probably want to look at it as more of a shunt capacitance because the coax is capacitive between its center and its outside. But again, sorry, I'm diverging a bit. We can see our SWR, 1.07. I think most people would be pretty happy with that. But as we get up to, again, that negative 20 dB point, we're getting to an SWR of 1.2. We're still mostly transmitting or mostly propagating our power forwards. But that's our attenuator. I'll throw the filter in so that we can take a look at that. And I've got a pop quiz. So I have a band pass filter here. It is centered at 1090 megahertz. And it's a mode S standard filter that we would use for ADS-B sensing. What is this going to be doing at 500 megahertz?
Stunned silence, Derek.
Much attenuation and blocking. So, okay. So we're seeing an answer that says that at 500 megahertz, and I'll put a marker there already, we will see very little gain. That it will block the forward propagation of the path. So if I put this on a radio and I transmit it through this, what would happen to the power at 500 megahertz? It would be reflected. Yes. And this is something which is deeply unappreciated. So here we can see our bandpass filter. And if I put down, I don't even know how to change markers here, sorry. I'll probably click these. Yeah. So we put marker 1 at one edge, at the lower edge of the pass band, marker 2 at the top end. We can see that between about 960 megahertz and 1.16 gigahertz, we have very low loss. I mean, I could do a bit better. If I go right into the middle of the pass band, we can see that we're actually losing, sorry, that's the green marker. Our forward gain, our S21, is minus 2 dB of loss, or minus 2 dB of gain. So we're losing 2 dB even at our signal of interest. But at 500 megahertz, where I had that question, we can see, and that's again green marker, so marker 2. At 500 megahertz, our impedance is just garbage. And our return loss, our gain is minus 50 dB. So good stuff. We're not propagating signal through, but our return loss is only 2.8 dB. Half of our power that is entering the filter is coming straight back, reflecting at us. So be careful how you build your filters. If you operate outside of their pass bands, a lot of the time they're reflective and will send the power straight back to your radio, being a terrible SWR. Now this is being smart enough not to try expressing this as VSWR, but which I don't know why. You should still get a value for that. But yeah, the power will come right back at you, and that can be deeply inconvenient. Now, that's not a correct result, which is why it's saying VSWR infinite, actually. This measurement, I've clearly bent the cables too much. The calibration is no longer valid. I should have gotten a filter that was in the better range of where this can actually measure well. The phase is clearly incorrect. We do not have gain here. It's a filter. It's not active. There's no way we could be getting more power returned than we're sending out. So this forward plot, I believe, the backwards plot is making a point that I wasn't expecting. I was expecting that to be below the line at least, but the punchline is you will get power reflected back. Now, I'm aware that I'm at the end of the time. I will definitely stick around. I'll come to the next point of the talk as well. I have one more piece that I'll plug in right now because I did promise time domain reflectometry, and I have not gotten to that. But what could be going wrong at this point? I mean, I've looked at this plot and I've said, okay, the band pass seems to be working pretty well. I believe that this has told me the frequency that it will work at. Great. It is showing me that it is attenuating signals out of band. Great, I believe that. This general shape of the noise floor, or kind of the gain floor, is following what it was when I just had my calibration loads there. I believe that. Looking at the S11 return loss, I know that I cannot possibly be getting more power back than I can't be getting more loss than I can't be getting an active signal back. I would believe the TDB return loss, so I'd have to calibrate. I would go back and recalibrate this and retest the measurement. Either that, or I'm having presenter head and I've flipped my negatives. Finally, last couple minutes here, I have a long piece of coax going across my room here, because the final piece that I wanted to get to was coax problem. What's the fault? We often have just long pieces of coax. You have it going up to your antenna, you have it going out of your shack, you have small jumper cables. You're going to need a better VNA for those. But you can measure a couple of things. You can measure your forward loss. You can say how much is being lost in my coax. We could do that 2-port measurement and measure S21. Great. You can do that on short lengths. You can do that on long lengths. Now, it's kind of hard to get the other end of the VNA up on your roof if you want to say, well, there's a problem somewhere between here and the antenna. Where is it? You could disconnect it, bring it down. But wouldn't it be nice if you didn't have to do that? Well, who here has heard of the Fourier transform? Is there anybody who's willing to throw their hand up in chat and say that they have? This is a mathematical operation, unfortunately. Yes, as someone who's had to deal with it too many years, I fully agree. This is an operation that takes a time domain sampling, which your software-defined radio could do, or many other conventional communication systems will do. Take a time domain sampling and then perform the Fourier transform on it and get your spectrogram plot. Where is the energy? What frequency is there energy at in this amount of time that I've measured? And so we have a time domain signal and we can transfer it into a frequency domain plot. Derek, my VNA is only measuring in the frequency domain. Yes, and it's measuring power and phase. We have a complex power measurement here, which is what the Fourier transform puts out. Okay, what happens if I do it backwards, Derek? We get time domain data. And so we can measure the VNA at many, many different regularly spaced points and do an inverse Fourier transform and get back a time measurement. Now, where were we at the beginning of this talk? We were watching voltage propagate in time down a line. So time equals distance. And at different frequencies, this Fourier transform will give us basically different time information. And so, propagation, the comments in chat, propagation delay, knowing the velocity factor of the coax, you can find the breakpoint. Yes, Yes, you can. I will do one more sweep here. I'm using the maximum kind of usable range of this VNA. It's done its sweep, and there's this time domain reflectometry button. And if I press this, it's showing me that between 0 and 5 meters, it's essentially a perfect 50 ohms. Does it actually tell me? It doesn't tell me the value at any point. That's a really, really lousy user interface. You do have to specify your velocity factor. Sorry, I've run out of time. I'll post a video of how you measure that with the NanoVNA. But this basically says how fast, as a percentage of speed of light, that voltage wave will move through your coax. And it's all about the different insulators and the spacing between the center conductor and the outer coax jacket, or outer coax shield part. You can see your standard LMRs and RG8s and et cetera here, as well as kind of some generic pieces. It's also not a huge range of values, so as I know that this is a pretty decent piece of coax. It's probably Teflon insulator, might be PTFE, but we can see that it's 5 meters long. Now, did I buy a 5 meter long piece of coax? Yes, I did. This is currently connected out to my it is currently just left unconnected. And so we can see that at 5 meters distance, the impedance is going off into infinity. It's an open circuit. This is what we're expecting. If I crimped the connector really hard at some point, we would see that that impedance would either drop up or down. Terrible plots. If you plot this in a more sensible program or you export this data and kind of look at it, you could look in a little bit more detail and be able to see that, you might see a discontinuity.
Derek, at that point, can I ask, is there a better VNA you would recommend than a NanoVNA for people looking to improve? Just trying to get, some concrete help for folk looking to move forward.
Yeah, so it really depends on your budget. The NanoVNA is brilliant if you don't want to spend more than a couple £100. Beyond a couple of £100, you get to like the Libra VNA, I believe is its name, which is pretty decent. There are some quite respectable ones once you get into the like £1,000 type range, either used Rigol or Siglent equipment that tends to get a bit bigger as well, but you're going to get more features out of them. It ends up being more precision, more stability. Because we can export all the data to software, if you're comfortable with software, the NanoVNA does give you kind of all the data. The data just isn't of stupendously high quality. Moving on past that sort of range, you get into benchtop equipment, which I wish I could show you, but my HP Hewlett-Packard era VNA would have been I've been looking at prices, I've been looking at repair components, about £3,500 to £5,000 used on eBay. You see lower frequency models of the same one coming up anywhere between about £700 and £2,000 for a used HP 8753 is the model number. We are getting to the point where used vector network analyzers, still in kind of the boat anchor form, are absolute steals for the functionality that they have, and fundamentally for the amateur radio market, their capabilities really haven't changed between the stuff that's now in the kind of couple thousand, 1,000 to 2,000, 3,000 pound range to the stuff that would cost 50 to 100 grand bought new from Agilent or Keysight. I guess
Sure.
now Keysight.
How are we doing in terms of the end? Do you want to take some more questions? Do people want to maybe pay another like 5 minutes and we'll do a few more things? I think we can
I
go
can
for it.
measure other devices and stuff, but I think it's probably more interesting if I just post some files and recordings in the chat. The last thing I'll say on the time domain reflectometry, this is a mislabeled slide, is as you increase the frequency span that you're covering, you get more spatial resolution. The smallest distance that you can discern a
Makes
change in
sense.
will
Yeah.
get shorter. And so these numbers are, of course, a bit ridiculous. You'll get 3 millimeter resolution if you go to 50 gigahertz span from your minimum frequency to your maximum frequency on your VNA. But thankfully, most of us probably don't need to care about a 3 millimeter distance. But you can see that this resolution increases as you go up in total frequency span. So always use the widest frequency span that you can when you're doing time domain reflectometry. This example from Keysight shows, trace one, if you can only measure 40 gigahertz of span, it's showing one discontinuity in this coax that they're measuring, or this trace. By the time they get up to 60 gigahertz, we can see that there's clearly two problems or two changes. This could be, two ends of a connector, for instance, a couple millimeters apart. Or this scale is like under a centimeter across the entire plot. Is more precision also needed? No, not really. Your sensitivity mostly matters when you're trying to do things. The sensitivity of a VNA largely isn't the constraining point for almost anybody. Once you're getting below -20, -30 dB of return loss calibration, which most things can get, is just enough to measure. If your attenuator is working to that degree, you can measure a 30 dB attenuator. Great. If your bandpass filter is rejecting at least 30 dB, that's probably enough for a lot of applications. And as we can see, a NanoVNA easily exceeds 30 dB of range. Calibrate often is going to be my punchline. Sorry we didn't get more. I will hang out and stop
By
trying to present
no,
more
by
pieces
all
here.
means, if anyone has questions, maybe chuck them on the recording of this. Maybe we can hang out there and answer some more questions. Derek, are you coming to pub?
Yeah, I'll follow along to pub.
Cool.
I'll hang out here unless if people want to talk specifically about this, or do you suggest that we move to
Well,
pub?
that's actually not a bad idea. One thing I was wondering if we want to, kind of have a little bit of an after hours session here for a short amount of time before people drift over to pub, that would work too. And that way people can learn a bit more as well before we potentially do a part two, which somebody has just helpfully mentioned there, which I may well tap you up for later on. Um, Thank you, Derek. That was really interesting. So far up to there was really interesting, and a few things I didn't know there as well. So that's great. Um, Derek Cazell, everybody. Is it bad I've never used a VNA? Not necessarily bad. Some people get away with things. Depends how much you're doing.
One of my favorite things about amateur radio is just how broad the hobby is. So
Of
I
course.
I I have not dug into my background. Why was any of this? Why should I have been talking about any of this? I've about a year and a half ago completed my PhD in RF power amplifier design. And
Hmm.
so, interestingly, one of the things I didn't get to here, which maybe is the relevant part too, is how do you measure active devices? Um,
Yeah.
because you get into a lot of pieces where even this small mini circuits, block amplifier that have here already puts out more power, enough power that it would damage the NanoVNA if you just drove it
Yeah.
directly in. Um,
Yeah. Absolutely.
but most of what I was doing was dealing with how these forward and reverse waves actually interact with each other, because you can get some really fun pieces where you actively drive power into the output of your amplifier, and it improves its efficiency, uh, which was a fun one. But
Cool.
yeah, running back through the chat if you don't mind.
No, no, we'll
Yeah.
we'll take this as our last action, I guess, and then we'll stop the recording.
Okay, so yeah, if you're doing HF and don't mind calibrating all the time, are you okay with a nano VNA? Yes, absolutely. For some of your measurements, you will need to take your device and physically turn it around so that you're swapping port 1 and 2 so that you can measure both your forward and reverse waves. Get your S22, which is the impedance of your port 2. This matters. Uh, this can matter in a variety of cases. You're limited to only measuring 2 ports at once, but that limitation stays until you get to a very high-end device. So for things like directional couplers, you have 3 ports, you would just end up measuring your input port to your output port as one set of measurements. Then you would measure potentially the reverse, so swapping that around in your VNA. And then you would swap it around again to get your input to your coupled port and potentially then you're coupled to your output port to get the
Sure.
full
Each
3-port
combination. Yeah.
piece. Yeah. But a NanoVNA below 300 megahertz, and
Mm,
this is the H4 model for anyone who cares. But I think basically all of them will do a great job on
yeah.
HF.
I
And
have
and they'll do a
the
great
V2
job
here.
on 2 meters, of course.
Yeah.
Uh,
Yeah.
they'll do a really acceptable job at VHF. I I'm I am very biased both from my professional work and my studies in that 1 gigahertz is kind of where I break away from DC. So
Yeah.
my mind is twisted. But anyone who's exploring the microwave realm,
Yeah.
it should be well aware that it just starts lying.
No, I mean, I have the V2 version here, which claims to go up to 3 gig. I got that because I started doing S-band microwave satellite stuff, and I mean, it works, but the results are all over the place,
Yeah.
very much so.
If you're going to invest in and your calibration, we didn't get into kind of how your calibration loads are, of course, never perfect. Um, in HF, yeah, your calibration loads are the next best thing to perfect.
Hmm.
It's hard to design a bad 50 ohm load at 50 megahertz. Same with open and closed. But uh, the calibration loads that come with the Nano VNA probably don't work all that great beyond 500 megahertz, beyond a gigahertz. And actually,
Yeah.
again, as a part two, maybe would be measuring all of these on a much better VNA and saying, okay, they claimed this was an open, but how well
Yeah.
does that actually
How
work
well
out to
does
a
that?
point?
Yeah. Can we take one more question before we stop at 10 past because it's a particularly oft answered question from asked question from beginners. Simon MD9WTR asks, when plotting SWR, I'm still unsure whether I should be calibrating with the open, short, and load at the antenna end or the shack side of the coax. I don't know. Lots of people struggle with that.
Okay. You should be the question comes down to where is the device that you're trying to measure going to be attached? If you're trying to measure the performance of only your antenna on its own, then you would need to calibrate all the way up at the top end of the coax. But if you're trying to measure something that's if you're trying to measure the performance of the whole system, what's your radio seeing? Your radio attaches to the coax inside of your shack. So you probably want to measure the whole thing. So you could calibrate right on, potentially the ports of your VNA, or in this case, to get to HF, I had to go through, 3 adapters to get from SMA to N because that's what I
Yep.
had, and then N to PL259. Um, and so I would calibrate, somewhere on this connector stack, basically.
Mm,
And then all the measurement that I then take is saying from this reference point at these connectors, looking up into the coax, going up your tower or up your house, what is happening? And so what you're hoping to see with an antenna is that it's very lossy at your signals of interest. You are losing all of your transmitted power, and that could be heat or it could be emitted waves. And I'll close on that. Yeah,
mm.
I'm realizing there's
All
so
right.
much more to be said.
No worries. Thank you very much, Derek. We'll stop the recording there. There is so much more we could do with this, and maybe we will revisit that and maybe look at a part two in the future. Thank you, everyone, for coming. We will be back in May. And just a reminder to let me know if you would like to do 10 minutes worth of something interesting or fun in June. We will take submissions. You can just DM me on the Discord. Cool. Thank you for watching, and we'll see you next time.